Now let's look at an example to see how we can calculate the power in the AC circuit. So assume I have a circuit like this, and assume um, so it has a source like that. So we know the V at the source is gonna be 10 volt with the angle of negative 90 degrees, and then it's gonna be connected to inductance that it has a um, um, that is L is um, zero point 0.1 henries, or um, um, and then it's going to be connected to the resistance with 100 ohm. So it's going to be 100 ohm, and then there is a capacitance here with uh, C is going to be 10 microfarad. So um, and assume we know the current in this one, so we know the current goes here. uh, so this one is going to be, the I is 0.1414 with angle of negative 135, and the I goes here, call it the I goes through the R, is 0.1 um, 0.1 amp with angle of negative 180, and the I goes in this one is going to be, the I goes through the C, and it's going to be 0.1 with angle of negative 90. And so assume this is what we have, and we want to um, calculate the power in this system. So the very first thing that we need to calculate that. If we didn't have the R, I, we should have calculated the I first. But here we have to go ahead and calculate the impedance for each of these three. So for the, I'm going to write it here. So for the ZL is going to be the J omega L, and also I think we have um, the magnitude of the omega. We have it is also, we know the omega is 1000. So the omega is 1000. So it's going to be the J times 1000 times 0.1, which would come at J100. For the Z at the C is going to be negative J over omega C, which is going to be negative J over 1000 times 10 times 10 to the negative 6, which comes at negative J100. And for the R, it's just R, which is 100. So I can go ahead and write this value here. So I know that the ZL is going to be J100. The Z at C is going to be negative J100. And the Z for the R is just 100. So So I have this, and now that I have this, I can go ahead and start to uh, calculate uh, the, the power in this circuit. So first of all, I would calculate the theta, and I know the theta is going to be the theta V minus theta I. So the theta V is the voltage source that is going to be negative 90. So I know that the theta V is negative 90, and the theta I is negative 135. So minus negative 135. So let me show you here also before I go further. So you can see here, this is going to be the theta V, which is negative 90. And this is the theta I, which is negative 135 degrees. So if I substitute them here, eventually what I'm going to get is going to be 45 degrees. So that's the theta I have. And I know that I need the voltage and the current, the RMS value of that. So I will calculate them before I actually go ahead. So I know the VRMS is the here the magnitude of that Vs divided by square root of 2. So it's going to be 10. So the magnitude of that, or the maximum of that, and by square root of 2, which is going to be 7.071 volt. And the same here, I can write the IRMS here is the magnitude of the I divided by square root of 2, which is here is 0.1414 divided by a square root of 2. So it will come out as 0.1 amp. So now that we have this, we can go ahead and calculate the power and the power that provided by the source. So I will say this is here the power delivered by the source. By source. So the power delivered by the source that I have here, the average power that delivered by the source is going to be the RMS value at the source, and this is the VRMS at the source, the RMS at the source. Right down here, so it's going to be VS RMS, and the same here is going to be the I at the source, the root mean square of that. The root mean square of IS. So it's going to be times IS RMS, the root mean square of that, and times cosine theta, which is going to be the 7.071 times 0.1 times cosine 45, which would comes out as 0.5 watts. The same, we can look at how much the reactive force delivered, so this is the average force delivered, and then the reactive force average is the V source RMS, I at the source, the root mean square of that, and this time sine theta instead of cosine theta. And it's going to be this 7.071 times 0.1 times sine 45, which is going to be the same as 0.5, but this time the unit is going to be the VAR, or VAR, volt amp reactive. So these are the power provided by the source. So we know that our source provided uh, this much uh, uh, power. Now that we know the source that provided this much power, we can go ahead and see how much power the other um, uh, the each element used. But before doing that, I want to just show you how we can calculate this with different methods. So I'll go power delivered by the source again here, power delivered by source, but this time use complex number instead of that the method we use pure. So this is the um, this is the second method of doing the same thing. So I can go ahead and say that the S is 1/2 of V I star. So I can go ahead and say the 1/2. So half of and if I go ahead here, so I know this is the VS and this is the IS star of that. So it's going to be, uh, 10 with angle of negative 90, and the IS star is going to be 0.1414, and with the angle is going to be the negative angle of I. So here the angle is negative 135 degrees, so it's going to be the 135 degrees. So it's a negative of that. And if you do the calculation, calculate all the numbers, and because it's a multiplication, just add the angle together. It's gonna come out as 0.707 with angle of 45. And then if I write it as a rectangular form, it's gonna come out at 0.5 plus j 0.5. And I know that the S is gonna be equal to P average plus J Q. So if I uh, compare this with this one, so this one is also have 0.5 plus J 0.5. So if compare these two together, so I can go ahead and say, okay, the P average is 0.5 watt and the Q is 0.5 bar. So it's another way of doing the same calculation that we did in the previous step. Now that if I want to want to see how much power delivered to this inductance. So we know that for the inductance, the average power that delivered to inductance is going to be 0. So the average is 0, but there's going to be the reactive power is going to be delivered to the inductance. So here, the power delivered to inductance. We want to see how much is that. So we know that the P average is going to be 0. So there's no no average power. The P average, let me put it here. The P average, the P average for the L is going to be 0. So there's no power provided, the average power provided to that. But it's going to be the, I would say the inductance power that's provided to that is going to be the I uh, RMS here squared and times the XL. And so we know that the RMS here is the same as the one that we have here. So it's going to be 0.1 amp, the power of 2. So that's one. And the XL here, the impedance for this one. So this ZL, because the R is not there, the ZL here is going to be the same as the XL because there is no R here. So this ZL is the same as the XL because only thing is there. So it's going to be times that 100. And then it's going to come out as 1.0 var. So again, I'm going to write the ZL. So I know the ZL is going to be 0 plus J100. And so this is the XL. So this with this sign, this is the XL with the sign. So the XL is going to be plus 100. So that's what we use the XL as a plus 100 here. And that's 0. Let me write it. Yeah. So that's 0 because I write to know that's a 0, but so that's the R that we don't have it in that ZL. So that's the R and that's the XL. So that's the power, the inductive, the reactive power delivered to inductance. The same here, I can go ahead and write the power delivered to capacitance. And so the IC RMS is going to be the magnitude of the IC divided by a square root of 2. We didn't calculate it here because the IRMS here was the same as the IRMS as the in the source. So this one was the same. So I just write it here so you know that. So this one was the same as I at the source. So we didn't recalculate that because it was the I that goes here was the I goes through the source. So it's very the same thing here. So it didn't calculate. But here we have to calculate the IRMS, the one that goes through this. So it's going to be 0.1 and then divided by the square root of 2. And then the Q is going to be here. So it's the QL. So the Q for the C. The same here is going to be IC RMS, the square root of 2. This time XC. And so we know that's going to be 0.1 the root of 2 to the power of 2. And the XC is going to be negative 100. I'm going to show you why. And then we are going to have the negative 0.5. Again, so this is the ZL that we have here. And then we can have the ZC is going to be 0 negative J100. We have it, so I will show you here. So the ZC is negative 100, so it would be the 0 negative J100. So then here again, let me, so it's not, so it's going to be 0. And then X, this sign plus this is XC is equal to negative 100. The sign and the magnitude. Here also let me rewrite that so you're not going to get confused. So it's the irons at this. This is the I at L or MS, which is the same at the source. The same here also, the P average for the C is also going to be 0. So there's no average current is going to be uh, go deliver to a capacitance that we can see here. So if you look at these two, we have 1 and -5 here, the QL and QC, and then we have the Q here. So basically all the Q provided here by the source is the same as adding the QL and QC um, together. So if I go ahead and say, to just double check if I can write it the Q, because it's only converted to the uh, delivered to these two. So just the value I have here, I know the value that provided by the source is 0.5, and the value delivered to this one is 1, and the value delivered to this one is negative 0.5. If I'm right, let me double check it. So yeah, it's a 1, negative 0.5, and then it's 0.5. So that's what you get here. And also I can go ahead and calculate the power. This is just a double check to do that, but I can also go ahead and calculate power delivered to resistance. And before doing that, I could have done it before. So if I come here, there's only one resistance here. I know all the average power is just used by the resistance. There's zero average power here, zero average power here. So I can simply, without calculation, says that whatever average power source provided is consumed by the resistance. So I can, without calculation, says, okay, the power provided to the resistance should be 0.5 watts, because all the power provided by the source should be delivered to the resistance, because these two are 0. But I can go ahead and calculate it to make sure that it's right. So I can go ahead and say, okay, the, the average power that delivered to the resistance is the, the current, the root mean square current goes, and then the R. And here we know that if we go back here, you know the current goes through, that's 0.1, so it's going to be 0.1 divided by the square root of 2. So it's going to be 0.1 divided by the square root of 2. So if I put these together, so the P average by resistance is going to be 0.1 divided by the square root of 2, the power of 2, and times with 100 ohm, which is the resistance. This gonna comes out as 0.5 watts. So all the average power delivered by the source is all consumed by the resistance in this example. Let's look at another example to see how we can use the power triangle to calculate the AC power. So again, assume I have a circuit like that with source equal to 41414 with angle of 30. So this is the voltage at the source, and then I have this one come here, and then I have a load that it is 10 kVA and the power factor of 0.5 leading. So this one, and then there is a second load here. And it is 5 kilowatts and the power factor of 0.7 and lagging. So and then we have, this is the I going here, and then we have the I goes down here. It's going to be I going through the load A. So if this one is the load A and if this one is the load B, so this is the power goes through that, so the current goes through, that's going to be I B. So assume this is what we have. So here we know that when we want to start that, so we know that the power factor here is the leading for the A. So for the A, power factor is leading. Therefore, it is going to be the capacitive load. For the B, the power factor is lagging. So it's going to be the inductive load. So the A is the capacitive load, the B is the inductive load. Now let's do the calculation. So we'll start from the load A. So let's see what happened here. So if I start from the load A, so the power factor is 0.5. So it means that the cosine theta is 0.5. So we know the power factor is cosine theta. And let me put it A here. So, so cosine theta at A is 0.5. So theta at A, the theta at the load A, or we don't need even to calculate that, so we can use the cosine theta directly. The average power, so delivered to A, we know that is going to be the VRMS the VRMS IRMS cosine theta. So it's going to be VRMS, and then it's going to be the current at A RMS, and it's going to be then cosine theta at A. So to calculate that, and then we know that this part, this part is the apparent power. We know that the apparent power is VRMS, RRMS, and we know the apparent power here. If you look at the A, so here we have it at the A. So this is equal to apparent. So the apparent power is 10 kilo VA. So this is the apparent power. So we know that. So this is the SA because of the unit. So we know that's the apparent power. And we know that the apparent power is actually equal to VRMS times IRMS, the magnitude of the So I just write it here. You know that the S, the magnitude of S is the VRMS times IRMS. You know that. So we substitute this part with 10. So it's going to be 10 times 10 to the power of 3. So this part. And then we have the cosine theta I is going to be 0.5. And do the calculation, so it's going to be 5 times to the 3 watts. Again, this VRMS or RMS is the S, and here, look at here, because we have the VA, we know the VA is the unit of the apparent power. So this is the magnitude of that S. So we can simply use that to replace these two magnitude there. Similar, just I'm gonna now I'm gonna let me go to the next page. Now I'm gonna just draw the triangle for the load A. So I know for the load A, we have the P average, which so it's gonna be the P average at the A. Then we have the Q, and we know because it's a we know that because it's the leading or capacitive load. It's going to be capacitive load. Sorry, let me rewrite that. Capacitive load. So we know because it's a capacitive load, the Q is negative. So basically, we know that here the Q is going to be negative. Here the Q is going to be positive. The Q at A is going to be negative, and the Q at B is going to be positive. So here also I have the Q at A, and it's going to be negative. And then this is going to be the S here, S at A. That we know. So we know the magnitude of S at A is going to, this is 10. Also we have, this is going to be the theta at A. So if I want to calculate the QA, one easy way of using that, so we can calculate the QA from the previous method that we have. But here I'm going to use this triangle to do that. So I know the, look at this triangle, the apparent square is going to be the P average at A square plus Q at A square. So therefore, this one I know is 10 square is equal that the P average from the previous step we had it was 5 times the, so it's going to be 5 times 10 to the 3. So it's going to be a square root of 5 times to the 3 square plus Q at A square. So if you go ahead and do this calculation, then the QA would comes out as 8.660 or 8660. But remember, this Q should be negative. So remember, it's going to be negative here. So it's going to be negative. If you go ahead and do the calculation, that's the value. So don't forget to use put the negative, because if you do the mathematically, it's going to come out as positive. But when you calculate this 8660, then put the negative sign in front of that to show that it is negative, because of the it's a capacitive force. So it's a Q for capacitive load is negative. Sorry, I think also I made mistake. This is the capacity. Make sure that make it correct as well. So don't forget to put that negative sign there. Now that we have this one, we can go ahead and do the calculation for the load B. Let's see how we can use the triangle to do the calculation for load B. So I'm gonna just draw the load B here. So I know it's gonna have some P average at the B. And then it has a QB, and because the Q at the B, because it's the inductive force, is going to be positive, and then it's going to be the S at point B. Now, if if I go ahead and look at here at the B, I have 5 kilowatts. So this one is 5 kilowatts here. Because look at the unit tells us what it is. So this one is P average at B, because the unit is the watt. Because the unit is what's the P average at the same here, because the unit was VA, we know that is going to be the apparent power. Here, because it's watt, we know that is the average power in that case. So I know that therefore the average power here is going to 5 10 to the 10 to the 3 watt here, and then this one is the theta B. That we have, and we can start to calculate that. So for this one again, we have the power factor is 0.7. So the power factor is 0.7. The power factor is the cosine theta. So we know that the cosine theta B is 0.7. And then the theta B is the cosine inverse or R cosine. The cosine inverse. So it's a cosine inverse of 0.7, which is going to come out as 45.57 degree. So this is the theta B. So now we know that theta B here, and we have that. So we can use this triangle to calculate the apparent power or the QB here. So look at the, if I want to calculate the QB, the tangent of the theta B is equal to QB divided by P average at the B. So I can go ahead and say that therefore I have the tangent of 45.57 is equal to QB, which we want to find. We don't know how much it is, divided by 5 times 10 to the 3. And then if I do this calculation, the QB would comes out as 5101 var. And because it's inductive, we keep the sign positive here. So we know the Q for inductive load is positive. So we keep a positive sign for that to make sure that we have the current. So we can use this triangle for the calculation of that. So here we have the Q, or the same. If we want, we also can calculate this S value. So also we are gonna, if we need it, we can calculate the S value for the B similar to that. So I'm gonna just write it here so that we can say the S value for the B is equal to square root of the P average for the B square plus the QB square if we need that. So we can do that. Next, um, uh, we want to see the uh, power delivered by, we calculate the power delivered by source. So the how much power delivered by the source in this case that we have. So if we go back, so how much power we want to mean how much power delivered by the source. So all the power delivered by the source is consumed by these two. So it's split between these two. So whatever this offer is absorbed by these two. So basically, the power delivered by this should be equal to adding everything that these two consume. So we can go ahead and say that the average power that the source delivered is the average power used by A plus the average power used by B. So I know that if I go back, so for each of them, the P average is 5,000. So 5,000, so simply just add them together. So it's going to be 5,000 plus 5,000. So it's going to be 10,000 watts because we use 10,000 watts in those two loads. So the source should be delivered 10,000 watts. Similarly, whatever the source the reactive power delivered should be equal to the reactive power that we have in used by those two elements. So we know that we have the negative 8660 plus 5110. So for the A and B, so you add them, so you end up we have 35 59 var. So these are the power. So basically we don't need to calculate them because we know how much delivered to each of the elements. We just add all the powers delivered to element to get the power delivered by the source. Mm, so now that we have what's happening at the source, we can go ahead and calculate the theta at the source. So here um, um, we can calculate the power factor, sorry, the power factor for the source. So we can go ahead and say that the theta is going to be the, again, if you can consider the triangle, so the theta is, let's put it, let me go back and look at it. That the tangent of theta is the q by the p divided q divided by the p. So I can go ahead and say tangent theta is q divided by p average. So therefore, the tangent theta is the q is negative 35.59, and then the p average is 10,000. And it's going to come, and therefore, if I calculate the theta from this, the theta would comes out as negative 19.59 degrees. And the same for the power factor is going to be the cosine theta So it's gonna comes out as cosine negative 19.9. So it would be 0.9421. So this is going to be uh, the power factor that delivered by the source. So we can say that. So for the source, the power triangle for the source also I can have it because we can have it so it has the P average at the source, which is 10,000. And then we have the Q at the source, which is going to be negative 35.59. And then we have this going to be the theta, which is negative 19.59. And then this is going to be the apparent power delivered by the source. So I can have this format. Now that I have it, so I can go ahead and look at it the same things that we have it here, just look at it as a complex format. So if I go ahead and say the power delivered in the complex format, so power delivered by source in complex form. So I can say that the S is equal to P plus JQ. So this is a P average plus JQ. So the P average is 10,000 plus J, and so it's a negative, so it's going to be negative J 35.50 59, or you can write it in the polar format as a 1061 with angle of that negative 19.59. Sorry. So no, this is 10 6 1 10 with angle of negative 19.59. It's going to be VA. Also, we know that the S is 1/2 of for the source is going to be the voltage at the source, and the I star at the source, or the I in this case is the I. The I goes at the source, so it's going to be, if this is going to be the VS, so I can go ahead and substitute there. So I know that the S, so this is the magnitude of the S that we have. So we know that's going to 10 angle of negative 19.59. So it's equal to 1/2 of the VS, which is 14 with angle of 30, and then I star. Therefore, if I calculate the I star here, the I star would comes out as so would be 10 6 10 angle of negative 19.59 divided by so 1/2 of 14 with angle of 30, and then it should divide the magnitude and subtract the angle, so it's going to be 15 with angle of negative 49.59. So the I is just the magnitude of the 15 and the negative of that angle. So it's going to be 49.59 amp. So this is actually how we can use the triangle, the power triangle, to calculate um, uh, the values that we need to calculate um, in this circuit. Remember that, just one thing before I go ahead, said remember that again, because we know here, when you calculate this angle, make sure that you use the negative sign here, because I use the negative sign, but remember that because the Q is negative, so the force is um, so we know that the Q is negative, therefore the theta should also be negative because of it's inductive. It is a capacitive. It's a capacitive load. So this is how we can use the triangle, the power triangle, to calculate, or basically to analyze the AC circuit.